we've seen that the power rule is very powerful. It can help us evaluate derivatives anytime I have x raised to any power. Whether that's a positive integer, a negative integer, a fraction, an irrational number, doesn't matter. However, the power rule doesn't help us with exponential functions. So I want to just compare two functions that at first glance look fairly similar, but actually behave very, very differently. Y equals x squared, that is a power function. There, the base is x, so the variable is in the base. The power, the exponent, that's what's constant. Okay. And in this case, we actually call this a power function. We usually reserve the name power function for when the exponent is a positive integer, although the power rule applies anytime the exponent is constant. But we do need to have this combination, that the base is the variable and the exponent is constant. Here, this is an exponential function. Those roles are reversed. The base here is constant. The exponent is where we have our variable. Okay. So very different type of function, easy to confuse because I'm seeing an exponent, but that's a power function, that's an exponential function. Now from algebra, we know that their graphs look very differently. Y equals x squared would be a parabola, y equals 2 to the x is an exponential growth function. So they look very different, and their rules as far as their behavior and the derivatives that describe those behaviors are going to be different as well. So in this video, we're going to explore the derivative of exponential functions. So an exponential function is y equals b to the x, just using b for that constant base. And the rules for it to count as an exponential function are that the base has to be positive. Okay? We don't allow for negative bases because those functions would have a horrific domain. Because if I have a negative number, I can't take any even root of it. So I would have to remove from my domain all x values that were fractions with an even denominator, and that's just a nightmare. Okay. 0 is kind of weird. I can't take 0 to a negative power. 0 to the 0 is actually 1, but 0 to any positive power is 0. That's kind of weird. Okay, but if I have a positive number, I can take that to any power. We are going to require that our base, however, not be 1. And that's just because if the base is 1, 1 to any power is just 1. That would be a constant function. So if I have y equals 1, I'm going to call that a constant function. I'm not going to call it an exponential function, even though I could write it as 1 to the x. Now what this does is this breaks our exponential functions up into two types. Okay, I've got y equals b to the x, where b is bigger than 1. If b is bigger than 1, that's going to give me exponential growth. Okay, so that's something like so. We've got a horizontal asymptote on the left side, and then our y-intercept would be at 0, 1, and then it just grows and it gets really steep really fast. The most common graph of exponential growth that we work with is the one with base e. So y equals e to the x is an example of exponential growth. We've also got exponential decay. That's the reverse pattern. That's something that starts big and gets small, so that the asymptote is on the right-hand side. That would be y equals b to the x, where the base is between 0 and 1. So for example, if I had 1/2 to the x power, that would be an example of exponential decay. But all exponential functions are one of these two types, either giving me exponential growth or exponential decay. What I would like you to do is pause the video and just sketch for me the derivatives of these. So if I were doing this, I would just erase this work. Directly below it, I'm going to try to sketch what the derivative looks like. So here's exponential growth. Here I would graph what does the derivative of exponential growth look like. Here's exponential decay. Here you're going to graph what does the derivative of exponential decay look like. So go ahead and pause the video, try and sketch that, and see if you notice something rather interesting. Welcome back. When you're sketching the derivative of a function, remember the first question we try to ask is the function going up or down? Well, with exponential growth, it's going up. Period. It's always increasing. So what does that tell me about the derivative? The derivative is going to always be positive. So when I sketch the derivative, it's always going to be above the x-axis. All right. Now, there are no transition points, so it's never 0 or undefined. And so I want to then think in terms of steepness. So I'm just going to label steep would be up here. Not so steep would mean that the slope was close to 0. Now I know down here, I've got another steep zone. This would be steep but decreasing. I don't need to worry about that because this is never decreasing. So I would look and I would say, okay, do we start out steep or not so steep? And it looks like we start out not very steep at all. So we're going to start out fairly close to 0. And then what happens is we get steeper. So as we move to the right, we're always going to be increasing. And following this backwards, it's getting less and less steep as we go backwards to the left, but it never actually completely levels out, so it never actually hits 0. So we do have a horizontal asymptote here. That's fascinating. The graph of the derivative has the same basic shape as the graph of the original function. Wow, that's a nice pattern. Let's see what happens with exponential decay. Now with exponential decay, if I asked are we going up or down, the answer would be down. Exponential decay, we are always decreasing. So when we graph the derivative, it's always going to be below the x-axis. Okay, so again, I'm going to just label my y-axis here. Not so steep is close to 0. This time, the steep zone I care about is the steep zone where the derivative, where the function is decreasing and steep, so that the derivative would be big and negative. So let's see, do we start out steep or not? So it looks like we start steep here, and as we move to the right, we get less steep. So I'm going to start out steep. I'm going to get less steep, which means I'm moving up, but I'm never quite going to hit 0. Now here, this shape doesn't look exactly the same as this shape, certainly, but it does look sort of like I flipped it over the x-axis. So exponential growth, the derivative has the same basic shape. Exponential decay, the derivative looks like the original graph but multiplied by a negative number. What this suggests is that for an exponential function, y prime is perhaps just some multiple, some constant of the original function. That would say that the rate of change is proportional to the original function. When two things are proportional, one is a multiple of the other. This suggests for exponential growth, the derivative would be a positive multiple of the original function. And for exponential decay, the derivative would be a negative multiple of the original function. Now, I'm not saying that they're just equal to each other, because I don't know that this is curving at exactly the same rate, but it has the same basic pattern. And this suggests that maybe this is in fact proportional to this. When this is small, it's increasing at a slow rate, so the derivative is small. When this is big, it's increasing at a fast rate, so the derivative is big. And the same thing can be said over here. When this is big, it's decreasing at a fast rate, so the derivative is big. It's just big and negative because this function was decreasing. And when this function is small, it's decreasing at a much slower rate, so the derivative is still a negative number, but it's a small negative number. Now, these pictures don't prove anything, but they suggest this very powerful relationship that we're going to see is actually correct. And this has huge implications in the scientific world. To have a function that changes at a rate proportional to its size, really, really powerful. Populations. If there are unlimited resources, populations are going to grow at an exponential rate. The more hedgehogs you have, the more baby hedgehogs are going to be born, and so the population of hedgehogs is going to grow at a rate that's proportional to the hedgehog population at that time. Exponential decay. Okay. In some cases, if you go to a doctor, the doctor might inject you with radioactive material. This sounds like a thing that doctors should not do. It sounds like it violates the whole do no harm principle. But sometimes they're injecting you with radioactive stuff so that they can do a scan and they can sort of see, is there anything really wrong going on inside you? And that's a little bit better than them just cutting you open to look inside and see if anything's wrong. Okay. But, very important, they make sure that the radioactive material decays at an exponential rate. So initially they inject you with enough that they can see what's going on, but very quickly the amount of radioactive stuff in you is decreasing so that there's not enough to really do any harm. Okay. So there are lots of things in the natural world that change at an exponential rate. Those of you who go on to take differential equations, you're going to see this all the time. The fact that exponential functions change at a rate that's proportional to the value of the function is really huge. It gives you, this is what we call a differential equation. It's a relationship between the derivative function and the original function. And you'd be looking for functions that would be solutions to that. Well, it turns out exponential functions are solutions to this. Exponential functions change at a rate proportional to their size. What we've done here suggests that. What we're going to do in the next video is use the limit definition of the derivative to suggest that a little bit further. Although exponential functions are complicated enough, we're going to have to rely a little bit on the mathematicians that have gone before to help us out with that.